For the CZ4041 project, we have chosen the Bank Russian housing market. And our group consists of Tong, David, Tony, and Ziyu. I'm David, and I'll start off with the problem and approach section. For the problem statement, Bank needs to forecast housing prices in order to better serve customers and make more informed decisions on housing projects. So the challenge is that given housing features and prices from year 2011 to June 2015, we have to predict the housing prices from July 2015 to May 2016. And we also have to use additional data, which is the macroeconomic factors during the years. So for the challenges, we found out that there are many features available, around a few hundred features, which is much more than other data sets. And many of them actually contain like bad or any values. And another challenge is also to figure out which regression technique is actually the most suitable. For our proposed approach, first, we want to explore the data and see if we're able to find any interesting or helpful patterns from the data, and also to perform feature engineering and data processing based on findings to create better data to train our models. Thirdly, we also want to experiment with different regression techniques and also perform hyperparameter tuning. And after tuning, we'll create the models for training and testing to benchmark the performance. And throughout this whole process of tuning and testing, we also want to adopt better data pre-processing methods. And then we combine the best models learned and also the best techniques to make further improvements. Finally, we leverage domain knowledge to make final improvements based on macroeconomic factors. Next, we move on to the data exploration section. The first thing we will do is to explore the data set and to find out more about these three main factors. Firstly, the number of missing values, then correlated values, and average price over time. For the number of missing values, firstly, we check on missing or null values in each column in our data sets. And then we found out that we have a total of 292 columns in our data set. And 51 of them actually have some missing values. And the number of missing values in these columns can range from 25 all the way to 14,441. Next, for the correlated values, we'll check the correlation with price doc in our data set. And features that display a high positive correlation includes full square, which is basically how big the house is, and also spot count. Then features with negative correlation includes nuclear reactor. So people wouldn't want to live near a nuclear reactor because it's scary and wouldn't want to pay more for it. Next, for average price over time, we can see that the average prices of houses increases by month and shows a steadily increasing trend, which is likely due to the inflation. Next, I'll pass on to Tony, who will talk more about the data pre-processing and feature engineering.
Okay, hi, I'm Tony, and I'll be talking more about data pre-processing and feature engineering done for our model. So, why do we need to do data pre-processing? Because we need to prepare our data to train our models effectively. We have done these 4 steps to help us prepare our models: dropping miscellaneous columns, removal of missing data, label encoding, and outlier removal. The first step that we've done is to drop miscellaneous columns in our dataset, because columns like the ID and timestamps are there to only help us organize the dataset, but it's not really relevant to help us predict the price doc. By removing these columns, we can help to prevent our model from picking up on any possible unrelated correlation that they might find from these columns. Next, we need to find a way to handle missing data. As some machine learning algorithms are unable to handle missing data, we've decided to drop these columns with missing data. However, models such as XGB and LightGBM were able to process datasets with missing data and even perform much better than compared to after we dropped the columns. Hence, specifically for these two models, we did not run the step of removing missing data. So This step ended up being optional, with some of our models having dropped the columns with missing data, and while some of them also retained the missing data. Next, we also need to perform label encoding, as most machine learning algorithms require numerical data to get our output. We had to convert categorical data into numerical values. There are various ways to do this, such as one-hot encoding or label encoding. In our case, we decided to use label encoding to minimize the number of columns we have in our dataset. Finally, we also perform outlier removal. Outlier removal was one of the main pre-processing steps that was done. From earlier during our data exploration, we found out that the full square feature is the feature that is the most strongly correlated to the predicted variable of price dog. So we determine our outliers based on this feature. So we calculate the price per square, or price dog divided by the full square, so that we can find out the price per square, and we remove the outliers based off this value to reduce the effects that they might have on our model. So any value equal to above like 600,000, or any value equal to or below 10,000 will be removed. So this will help us to reduce the number of irregular training data that exists in the training data and give us a more proper prediction. Next, we'll be talking about some of the other drop methods that we tried but ended up not using. So the first one was to try and replace missing data with the median values in the column. So although we tried this, the results resulted in the accuracy of our models decreasing, and we ended up not using this method. The other method that we found that many people suggested was to separate the product type column into two based on the owner occupied and investment training model. However, it also has resulted in our model accuracy dropping, as shown in the picture below. The XGB output combined is a result of us having trained two different models and has a higher error than the XGB output, which is the result of our one single model. Next, I will let Zhiyu to talk about the next part of our project.
Hi, I'm Ziyu, and I will be talking briefly about the technique selection, tuning, and testing. After some research, we decided to experiment with the following 8 regression techniques, all of which are available in the sklearn library. The algorithms were selected as they are commonly used for regression problems. After selecting the algorithms, we performed parameter tuning. The linear regressor was very simple and no parameter tuning was required. For the other algorithms, we used 2 different methods for the parameter tuning. The first method is to use cross-validation with different hyperparameter combinations. We first select a set of hyperparameters we want to tune and a combination of hyperparameter values we would like to try. We then use a loop to iterate through all the combinations of hyperparameter values we selected and perform cross-validation on each of them. We then manually select the hyperparameter values which had the lowest mean squared error. This method is quite thorough but very time consuming and not feasible on some of the more computationally intensive algorithms like the multi-layer perceptron. For more computationally intensive algorithms, we use the second method, which is to manually tune the hyperparameter values of the algorithm. For this method, we first test the performance of the algorithm with the default values. We then adjust the hyperparameter values according to the results we got from the experiment and our knowledge of the algorithm's hyperparameter. This method was much less time consuming and more suitable for computationally intensive algorithms. Once the hyperparameters are finalized, we train the model on the pre-processed data. We then use these 3 models to make predictions on the test dataset and submitted the predicted values to the Kaggle competition to get the root mean square log error score for each of the model. Once we have all the scores, we reviewed the results. And from the results, we found that the top 3 models in terms of root mean square log error to be LightGBM, XGB, and gradient boosting regressor in that order. Meanwhile, the linear regressor and support vector regressor performed poorly for this problem, as there were negative values in the final prediction. Due to this, they are excluded from further experiments. And from the table, you can see the final root mean square log error for each of the models. Next, Kong will talk more about the further improvements to the models.
Hello, I am John. So now I would like to talk about further improvements. So next. So given all the knowledge gained from testing and tuning, we decided to combine the techniques together to see if there is any performance improvements. So there are three methods that we have tried: weighted average, and stacking. Next. Next, please. Yes. So for weighted average, a simple average of the trained model results are used. However, it gave poorer performance compared to the results outputted by like GPM, SG, and SGP models. Next. So for the weighted average of the model results, we give more weight to the models with better performances. Some really poor models, such as those using linear regression or multi-layer perceptrons, are removed. Finally, after some experimentation, we decided to stick with the final formula, which is 0.4 times FGP model result plus 0.6 times FGP model result, and this gave a published score of 0.31338. So next, for stacking, we use the base learners. There are two steps. First, we use the base learners to generate new features, and then we train a new meta learner from these new features. Next, please. So regarding creating new features for individual learners or individual technique, we found that if we use a model trained from on the whole training set to output the results for both training set and test set, we may encounter overfitting. Therefore, we decided to instead create 5 models for every technique. And this process of training these 5 models can be seen in the diagram. So you can see that for model 1, the model 1 will be created from training on the first 4 parts and then perform prediction of the part 5 and test set. The same happens for other models where they were trained from the 4 parts, and then we make prediction on the remaining training part and the test set. The prediction on the training parts will combine to form prediction for the training set, and results from the test set were also averaged. Next, please. After that, we train a meta learner, so the features are created from algorithm XGBoost, random forest, AdaBoost, gradient boosting, and LightGPM were combined. And then we use the XGBoost meta learner. So as a result, we come out with a better score than that of weighted average. Next. So after all these combinations, we found that the weighted average and stacking performed best. So with these results, we wanted to improve by using micro factors. So actually, by using domain knowledge, we realized that there was a link between GDP growth and real estate market, and that's why we decided to multiply the predicted price by the expression of related to GDP quarter growth, as you can see on the slide here. And the results from stacking did improve. However, the result by weighted average improved to reach a published score of 0.31123, which is in top 23%, and it is a best score. So next. So in conclusion, throughout this project, we realized the importance of proper data cleaning, and we also know how to approach hyperparameter tuning given limited time, and we also explore different ensemble learning methods. And in the future, we may improve on our models by performing more data cleaning and feature engineering. And that's it for our presentation. Thank you for listening.